All right, so for this video, we're going to be covering example problem 5.19. It's topic number 50. So in this problem, we have a rod that goes from point A along point B to point B, and then from point B to point D. All right, so we can draw our coordinate system, be our standard 3D coordinate system of an x, and y, and our z axis. All right, and then we are given the information that at point A we have a journal bearing, and we're told at point D we have a ball and socket joint. All right, and then we are told that we have a weight of a mass of 100 kilograms, and we have a cable from point B to point C that is supporting this structure. All right, so we're asked to use only one equilibrium equation to attain a direct solution for the tension within BC. All right, and we're also said that the bearing at A is capable of only exerting force components on the Z and the Y direction since it is properly aligned along the shaft. All right, so let's draw our free body diagram first. All right, so we're going to draw our free body diagram of A, B, C. All right, so if we draw that diagram, here we'll first draw its outline shape. All right, the second step, we'll define our coordinate system. All right, third step is we'll apply any known forces. So we'll have a force in the z direction, so I'll call this force W, which would be equal to negative 9.81 meters per second squared times 100 kilograms. All right, and that would be along the k direction. All right, we have, in addition, we have reaction forces due to the different support structures. So at the journal bearing, we were told that it only applies a force along the along the z and the y directions. So in that case, we would have one force AY and one force AC. All right. And then for the cable from point B to point C, we know the direction of that force would be along the z axis. So I'll say that force TBC would be equal to the magnitude times the positive k direction. All right, and then our last part here is we have a ball bearing at D. So ball bearings resist translation in every direction. So we can relate this as dx, dy, and dz. So we know that we have a few dimensions here. I'll try to add. All right, so that should be all the information that we would need to help solve this problem. All right, so once we have our free body diagram complete, what we would then do is we would apply our equilibrium equation. All right, so what we can do here is we can draw an axis from point A to point D. All right, so if we draw an axis from point A to point D, what we'll notice is that the majority of our forces, we have a force in the x direct, we have most of our reaction forces act along this axis, right? The only force that doesn't act along this axis is TBC and our weight. All right. So to allow for equilibrium, all right, what we can do is instead of solving for doing all of our different equilibrium equations to solve for TBC, what we can do is we can, instead of using all of these different equations, what we can do is we can say the sum of all the moments about the AD axis must be equal to 0. Okay, so the moments about the AD axis are only caused by the moment about the AD axis due to the tension in BC, plus the moment about the AD axis that's caused by the weight. All right. So the moment about an axis is a scalar number, so we don't have to, these will not include any hat terms here. These are both all scalar values. So we can write, we'll write our moment, we'll do the moment due to AD CC first, right? So we know that a moment about an axis is equal to the unit vector for the axis, all right? All right, the dot product of the unit vector of the axis, all right? All right, times the cross product of our force and our position vector. All right. So in this case, our position vector would go from any point along the axis AD to where our force is being applied. So I'm going to pick from point A to point B. All right, so I'll say this would be RAB. All right, so our next row would be the X, the Y, and the Z component of RAB. Since point A is from point A to point B would be going along the positive x-axis, 1 meter. All right, and then it has no component in the z or the y direction. All right, and then the force along this direction, along this axis, would be equal to the tension BC. All right, so that only has a component along the z direction. Right, so there's no x and y component. Right? So if we evaluate this determinant, what we end up getting 0, 0, and TBC. All right, so the unit vector UAD would be equal to the RAD divided by the magnitude of RAD. So the RAD is equal to point D is at the origin, so it would just be equal to RD, which is 0, minus the coordinates at point A. So point A is along negative 1 meter and negative 1 meter in the x direction, and there's no change in the z direction. So the magnitude of that would be 1 meter squared plus minus 1 meter squared, and we'd end up getting square root of 2. So we end up getting UAD would be equal to the square root of 2 over 2. Negative square root of 2 in x and negative square root of 2 over 2 in j. All right, there'll be no z component. All right, so we'll plug this in to our equation here. So we get minus radical 2 over 2, minus radical 2 over 2, and we get 0. And we're just going to copy the first two columns to evaluate our determinant. So if we evaluate our determinant, we'll take diagonal values first. So these all end up being 0. Then we take our diagonal values going back, and we get one term that's non-zero, which is this term. So we have to include an additional negative sign, so it'll get MAD DC would be equal to negative minus radical 2 over 2 times 1 meter times TBC. Or we end up getting radical 2 over 2 meters times TBC. Right. So we would repeat the same process for the moment about due to the weight. So the moment about axis AD due to the weight would be equal to the dot product of UAD times R, the cross product of R and F. All right, in this case, R UAD would be the same, so it'd still be equal to minus radical 2 over 2, minus radical 2 over 2, and 0. All right, the position vector R we could do from point D to point C, or point E, where this is applied. All right, and then so that would be equal to just minus half a meter along the y direction. All right, so and then we get for our force is going to be our weight, so it's known minus 981 newtons, and then we have no x in the y component. All right, so we include the radical these two forces here, or the two. We're just going to copy the first two columns again, and to evaluate this equation. All right, so when we evaluate this equation, well, again, take the diagonals. So again, we're going to get a lot of zeros. All right, and then we'll go back along the opposite directions. So we end up with only one non-zero term. That was this first diagonal here. So we'll end up getting MADW is equal to minus radical 2 over 4 times 981 newtons, which is going to be equal to which is going to be equal to which we'll just keep as being right. We'll write it as minus radical 2 over 2 times 490.5 newtons. All right. So what we can do is we know that if we go back to sorry, this should be Newton. This should be Newton meters, not newtons. And then we should end up getting. If we go back to our original equation here, all right, we're going to just add our two terms together. So we'll have 0 is equal to radical 2 over 2 meters times TBC minus radical 2 over 2 times 490.5 newton meters. All right, so what we end up getting here is we would get TBC times radical 2 over 2 meters would be equal to radical 2 over 2 times 490.5 newton meters, and then we would get TBC would be equal to 490.5 newton meters. All right, so to summarize this problem, we were able to simplify. So once we drew our free body diagram, we recognized that there was an axis that that most of the applied forces were along. So we could take the sum of the moment about those axes to isolate our one unknown force we were interested in, which was TBC. And once we did that, we could calculate. You were able to use the moment about an axis formula to calculate our unknown force, and able to solve for the magnitude of the tension within that section. All right, so that concludes all the videos for lecture 15, and I look forward to hearing any feedback you have from these videos. Thanks.